We've seen before that given a function y equals f of x, we can give an approximation of this function by the tangent line, or the linearization. This gives us a reasonable approximation for near the value of x equals a, where the tangent line is taken at. So let's quickly review that, because we're going to see Taylor polynomials are a way to improve that approximation with higher degree polynomials. So to quickly review linear approximation, we can approximate a function y equals f of x near the value x equals a by its tangent line approximation, assuming we can evaluate f of a and f prime of a. So in this case, we write L of x. We wrote L of x for the tangent line approximation before. So it's natural to ask, well, what if we used a higher degree polynomial? There's no reason we should necessarily have to stop at a line for higher degree or for approximations. So before we go to higher degree polynomials, though, let's note a couple of important things here. If we plug in a into L of a, let's look back at that. If I plug in a, then that second term has an a minus a in it, so that will go away. So L of a is just equal to f of a. And similarly, if I take the derivative of L of x, that'll actually be f of a everywhere. So in particular, L of prime of a is equal to f of a. So notice here, f of a and f prime of a are constants. So when I take the derivative, really I'm only taking the derivative of x there. Everything else is a constant, and the coefficient of x is just f prime of a. So that gives us this result on L prime of a equal f of a. So what this tells me is that the function and the linear approximation have the same value and the same derivative. So in particular, we can also say that this would tell us that not only are the values equal, the function and the linear approximation are either increasing or decreasing together. So going forward, since we're going to generalize this linear approximation to higher degree polynomials, and our linear approximation has degree 1, we're going to write p1 of x for that linear approximation, and we'll refer to this as the first degree Taylor polynomial, or the first Taylor polynomial. So the next step would be, suppose we want to do a degree 2 Taylor polynomial. So we want to approximate our function not by a line now, but by a quadratic. So let's suppose we have a quadratic of this form. I could just tell you what the coefficients are here, but let's go ahead and go through and kind of see where those coefficients come from for this one. So let's suppose we don't know the coefficients. We just say C0, C1, and C2, and we want to figure out what these coefficients are. Now, what properties do we want P2 of x to satisfy? Well, when I evaluate it at a, I want it to be equal to f of a, so the same value. I want the derivatives to be the same, and I want the second derivatives to be the same. So first thing is the value, second thing you can think of as increasing or decreasing the same, and the third thing you can think of, we want the concavity to match up. Remember, the second derivative is telling us concave up versus concave down. So I want my P2 of x to satisfy those three conditions, and those three conditions will be enough to determine C0, C1, and C2. So let's see how that's done. So first note, if I if I plug in a for x, I get an a minus a and an a minus a squared. Those are both 0, so this just gives me C0 back. Now we recall we wanted P2 of a to be equal to f of a. So if P2 of a is equal to f of a and is equal to C0, that tells me C0 must be equal to f of a. So that gives us our first coefficient of the polynomial. Now if we take the derivative of P2 of x, we're going to get C1 plus 2 times C2x minus a. Now we use the fact that we wanted P2 prime of a to be equal to f prime of a. So in particular, if I plug in a, that second term is going to go away because I get an a minus a term. And then I know that I want this to be equal to f prime of a. So that tells me C1 must be equal to f prime of a. So that gives us our second coefficient. So if we stop here and plug in what we found so far, we have P2 of x is equal to f of a plus f prime of a x minus a plus C2 times x minus a squared. But notice those first two terms, the f of a plus f prime of a x minus a, that's exactly the tangent line approximation, which we denoted as p1 of x. So the degree 2 Taylor polynomial turns out to be just the degree 1 Taylor polynomial plus a quadratic term. So now we just need to figure out what that C2 coefficient is. So we're going to do the same procedure. Now notice we have the first derivative at the start of the slide here, that p2 prime of x is c1 plus 2c2 x minus a. So if I take the second derivative of that, I'm going to get just a 2c2. And now remember, it doesn't matter what I plug in for x here because this is a constant. So p2 double prime of a is going to be 2c2, but I wanted it to be f double prime of a. So that means we should have 2c2 being f double prime of a, or solving for c2 should be f double prime of a over 2. So that means my degree 2 Taylor polynomial is f prime of a plus f prime of a x minus a plus the second derivative of f evaluated a divided by 2 times x minus a squared. And this polynomial satisfies that it's going to have the same value at a as f, the same derivative at a as f, and the same second derivative as at a as f. Now we can continue on. We could go ahead and compute this for a cubic, a quartic, and so on for any degree polynomial we want. And so we'll go ahead in class, we'll go through and do P3 just to make sure it solidifies kind of where the coefficients are coming from, because there's going to be a little bit of a change going from 2 to 3, which we'll see. But for now, for this video, we're just going to give the general formula without justifying it, and then we'll see some pictures. But first, we need a little bit of new notation before we can do this. So we can't keep putting primes on the f forever because there gets to be too many of them. So instead of putting a bunch of primes, we'll just put the number of derivatives in parentheses. So if I wanted to take the nth derivative of f, I'll put f and then the power n, but make sure that n's in parentheses so we know it's the derivative. So for example, instead of writing f double prime of x, I could write f with a 2 in parentheses of x. The other thing we need is the factorial function. So n exclamation point, which is read n factorial, is just n times all of the smaller integers all the way down to 1. So n times n minus 1 times n minus 2 all the way down to times 2 times 1. So for example, if I did 4 factorial, you start at the 4 and you multiply all the way down. So 4 times 3 times 2 times 1, which gives me 24. So with that, we can just write out what the degree n Taylor polynomial is. And it's just this thing. So we did the first 3 terms already, but just notice after that, we start having, so the next term after the second degree, or the degree 2 term would be the third derivative of f evaluated at a divided by 3 factorial times x minus a cubed. And we keep doing that all the way until we get to the nth term. So we'll spend more time on this in class, but let's go ahead and see some pictures to kind of see why we might want higher and higher degree Taylor polynomials and how they give us better approximations, and they let us let x be a little bit further away from a with the higher degree polynomials. So here we have the sine function, and we're going to take a to be pi over 4, so we know how to evaluate that. And here I've graphed the linear approximation, or the first degree Taylor polynomial. And we can see as long as x is pretty close to pi over 2, this is a pretty good approximation. But once we get further away, like if I was looking at x equals 5, this is a terrible approximation. So then I could say, okay, well, what about the degree 2 Taylor polynomial? And we can see this gives us a little bit better range. It's still not great at 5, but if we go over to like 3 or 4, this is a pretty good approximation. So you say, okay, well, what about the cubic one? We can see this is a little bit better because it can change directions. We could go to degree 4. Again, it can change direction, so it gives us a little bit better approximation for a larger interval. And we can keep going higher and higher. So I graphed the 15th degree one here, and we can see it's so good between minus 5 and 5, it pretty much overlaps with the function completely. So if I want to get a value of sine that's for any of the values of x between minus 5 and 5, I can plug those into a degree 15 polynomial, which is very easy to evaluate, especially for a computer, and it will give me pretty much the exact value of the sine function there. And so you can see the higher degree polynomials are going to, in this case, are going to continue to get better and better.